Okay, in today's lecture, we're going to cover the section 6.3 material on conservative vector fields and a result known as the fundamental theorem for line integrals, which gives us a simple way to evaluate line integrals of conservative vector fields. So let's recall a little terminology that we had introduced in section 6.1. We had said that a vector field F is said to be a conservative vector field if it can be considered as the gradient of some scalar function. So what that means is a vector field is conservative if there exists some function f such that the gradient of f is equal to this given vector field. And in this case, the function f is said to be a potential function, or sometimes called a scalar potential, for that vector field. Now, conservative vector fields have some very nice properties, which we'll explore in this section and throughout the rest of Chapter 6. So a question of interest becomes, how can we tell whether a given vector field is conservative? So of course, I know if I find the gradient vector of some function, whatever vector fields I get is conservative because it was the gradient of some function. But if we're just given the vector field, how can we determine whether there exists a function whose gradient would be equal to that given vector field? So in this section, we're going to introduce a theorem which allows us to determine whether a two-dimensional vector field is conservative. But to state that theorem, we first need to introduce a little bit of terminology. So let's start here by introducing some definitions. We would say that some curve is said to be closed if its terminal point is the same as its initial point. And moreover, a curve is said to be simple if it does not intersect itself anywhere between its endpoints. So to illustrate these definitions, let's look at some plane curves. So if we considered a plane curve C, which looks like the following. Let's say it's traversed in a counterclockwise direction, where our initial point, this point that we start, ends up being the same as the terminal point. So let's call this the initial / terminal point. This would be an example of a closed curve, since the initial point is the same as the terminal point. And this would also be an example of a simple curve. So this is an example of a closed simple curve. It does intersect itself at the initial / terminal point, but as we traverse this curve along this direction, we see that it does not intersect itself anywhere between that initial and terminal point. So it would be considered simple in this case. So other examples to illustrate this, if we had a curve, let's say, that had its initial point and terminal points given here, maybe traversed in this direction. This is an example of a curve which is not closed, but it is simple. It does not intersect itself anywhere between those endpoints. But of course it is not closed since the initial and terminal points are different. So some other examples, let's say that we had a curve that was something like this, say C, which is traversed in this direction. So this would be an example of a closed curve, since its initial and terminal point are the same, but it is not simple. We see that there is a point between that initial and terminal point where it is self-intersecting. So here, this would be an example of a closed curve, which is not simple. And for, I guess, our last case here, we would consider maybe a curve that looks like this, which has its initial and terminal points labeled. It's traversed in this direction. So this would be an example of a curve which is not closed and also not simple. All right. So illustrating the idea of a closed curve or a simple curve. So a little more terminology which we'll need here is the following. We would say that a region D in the plane is said to be open if for any point P, which lies in that plane region, there exists some disk centered at the point P, which lies entirely in our region D. So to illustrate the idea of a open region in the plane, let's suppose that we had some plane region that looks like this. Let's call this region D. So for any point P that I choose within this set D, let's call that point P, looks similar to my D. Let me make my D a little more distinct here. We would be able to find a disk which is centered at that point that lies entirely in D. So another way to define a open set, it's any set which does not contain its boundary points. So if I were to include the boundary as part of this region, well, if I choose a point P on the boundary, of course, any disk that I would include around it would include some points that lie outside of D itself. So any set which does not include the boundary itself would be considered a open set. So one way that we might denote this a little more clearly would be to do the following. Rather than drawing this set as we did here, to denote that we are not including our boundary points, we can sometimes use like a dotted line for the edge of the curve here. So this would be an example of a open region. Now some other definitions which we could consider for regions would be the following. A region D is said to be connected if any 2 points in that region can be joined by a curve that lies entirely in D. So the example that we've already shown here is also an example of a connected set. If we were to consider 2 points in this region D, let's call them P1 and P2, there is a curve C which connects those 2 points that lies entirely within our region D. So this would be an open connected region. Now, an example of a region which would be disconnected might be some region that consists of 2 distinct pieces. Let's say something like this, where D would be the union of these 2 plane regions. So we would have, for instance, if we chose a point P1 in this first region and P2 in this second region, there is no curve that lies entirely within that region that connects those 2 points. We would have to move outside of that region for any curve to connect these 2 points. So this is an example of a region which is disconnected. Now, the last thing that we'll talk about for a plane region, or the last bit of terminology, is that a plane region D is said to be simply connected if it is connected and every simple closed curve within our set encloses only points that are in D. Or more simply, we can think about a simply connected region in the following way. It is a connected set which also has no holes in it. So this first example that we had illustrated, it is a connected set and there are no holes within this set. So we would also say that this is simply connected. So what would be an example of a connected set which is not simply connected? Well, let's see if we can illustrate it here. Suppose that we have some region D, but it has a hole in this region. So maybe there's some little sub-region which we've taken out from this plane region. So this is an example of a connected set because any 2 points in this set can be connected by a curve which lies within the set, but it is not simply connected. Now, why not? Well, the definition of simply connected says for any simple closed curve within D, it encloses points that are only in D. So here it fails that definition because if I were to consider the simple closed curve shown here, this curve encloses points that lie in this hole. That is, points that lie outside of the plane region D. So this would be an example of a set which is not simply connected. So finally, now that we have this terminology, we can introduce a theorem which allows us to determine whether a vector field is conservative in the plane. So here's what our theorem says. It's called the cross partials test for a conservative vector field. It only works for two-dimensional vector fields. So let's consider a two-dimensional vector field. Let's say f of xy has component functions p and q of xy. And this will be a vector field defined on an open simply connected region D in the plane, where these component functions p and q have continuous first-order partial derivatives. So this theorem says that the vector field f with those component functions is conservative if and only if these partial derivatives are equal to each other. That is, if the partial derivative of our first component function, p, with respect to the variable y, is equal to the partial derivative of q, the second component function, with respect to x. So this is known as the cross partials test. If we differentiate the first component function with respect to y and the second component function with respect to x, this vector field is conservative as long as those are equal and it's being defined over an open, simply connected region in the plane. So let's look at an example where we're given a vector field and we are asked to show that it is conservative. So in this next example, we have the following vector field, f of xy, which is two-dimensional. This first component function we could call p of x and y, and our second component we would call q of xy. And in part A of this example, we're asked to show that this vector field is conservative. So for two-dimensional vector fields, we have this cross partials test. So let's check it out. Here we would say since the partial derivative of p with respect to y is equal to, if we differentiate p with respect to y, we have e to the x cosine of y minus 1. And if we differentiate q with respect to x, we have e to the x minus 1 times, or e to the x cosine y minus 1, which is indeed equal to this partial derivative. So since the partial derivative of p with respect to y is equal to the partial derivative of q with respect to x, we know that this vector field f is conservative. So that's what we wanted to show in part A. Now let's recall what exactly have we shown here. What does it mean to be conservative? So that means that our vector field f of x and y is equal to the gradient field of some scalar function f. And recall that that gradient would have a first component given by the partial derivative of f with respect to x, and the second component would be the partial derivative of f with respect to y. So in part B of this example, we are asked to find a potential function for f. So that is, we want to find the function, the scalar function, little f of xy, such that the gradient of that function is equal to the given vector field. So let's think about how we're going to do this. So in order for our vector field to be equal to a gradient vector field, we know that the first component of this vector field, that is the function p, has to equal the partial derivative of the potential function with respect to x, and the second component, q of xy, has to equal the partial derivative of the potential function with respect to y. So we'll start by setting those functions equal to each other. We know that whatever our potential function f is, its partial derivative with respect to x has to equal the first component of our given vector field, that is e to the x sine y minus y, and the partial derivative of the potential function with respect to y has to equal the second component function of our vector field, that is e to the x cosine y minus x plus 2 times y. Now, if we know what the partial derivatives of this function f are, we ask ourselves, well, how can we find f itself? So if we know what the derivatives of a function, to find the function itself, we would need to find antiderivatives. So there's a couple of ways that I could proceed here. Our potential function, f of xy, we could find one way by taking the antiderivative of the partial derivative with respect to x, which was e to the x sine y minus y. And since that was the derivative with respect to x, we would need to find the antiderivative with respect to x. That is, we have dx on the end. So let's see if we can find our antiderivative here. So with respect to x, we're treating y as a constant. So here the antiderivative of e to the x sine y, well, the antiderivative of e to the x is e to the x, and we're multiplying by a constant sine of y, minus y is a constant, so the antiderivative with respect to x is that constant times x, that is xy. Now, this is the first example that we've looked at in this course where we're looking at a indefinite integral of a multivariable function. That is, we don't have limits of integration on our integral here. So recall, to evaluate a indefinite integral, we need to include a constant of integration on the end. But now in the case that we're working with a multivariable function, if we're finding the antiderivative with respect to x, a constant with respect to x would be any function that only depends on y. Because if we were to differentiate any function of y only, that is g of y, with respect to x, we would get 0. So we can verify that if we were to take the derivative of this function that we just found, we would get back the partial derivative of f with respect to x. So now the question becomes, well, what is this constant function, g of y? So recall there's another condition that needs to be satisfied here. We need the partial derivative of f with respect to y to be equal to the second component of our vector function. So let's make sure that condition holds. So what we just found was a general expression for our potential function f of xy by finding the antiderivative of f sub x. So if we look at the partial derivative of this function with respect to y, we would have e to the x cosine y minus x plus the derivative of this g of y function. We'll call it g prime of y. And this partial derivative of f with respect to y here better equal the second component of our vector field in order for this to be conservative. So setting this equal to that second component, we have e to the x cosine y minus x plus 2y. And so to solve for g, well, let's see what we can cancel here. On both sides of this equation, we have an e to the x cosine y, so those terms will cancel. We have a negative x, so those terms cancel. And we're left with g prime of y is equal to 2y. So if we know the derivative of y to get g of y, we would find the antiderivative of this function with respect to y. So the antiderivative of 2y with respect to y would be y squared plus some arbitrary constant c. So now, taking this expression that we just found for g of y and substituting it back into this expression that we found for f of x earlier, let's see what we have for our potential function. So we had f of xy was of the form e to the x sine y minus x times y plus g of y, and we just found g of y to equal y squared plus some constant. Now, in general, this potential function could depend on any arbitrary constant c here. So unless we have some other condition that we have to satisfy that would allow us to solve for c, to make a simple choice for a potential function, we could always choose the one where our constant c is equal to 0. So this would be a potential function for the given vector field. So in part A of this example, we use this cross partials test to show that our field was conservative. And then using the component functions of that vector field and what we know about the gradient, we knew that our partial derivatives of the potential function were equal to those component functions of our field. So by finding their antiderivatives, we were able to find this potential function f. Now let's see why we might care about that. Why do we care about finding a potential function for a conservative vector field, or why do we care about showing that a vector field is conservative at all? So the reason is that we have a very nice property for line integrals of conservative vector fields. And this result is known as the fundamental theorem for line integrals. So it's very similar to the fundamental theorem of calculus. Let's look at how this works. So here's what our theorem says. It says if we have a smooth curve C, which is defined by some vector function r of t for values of t ranging from a to b, and f is a continuous conservative vector field. So it must be conservative for this theorem to apply. And the potential function of that conservative field is a scalar function little f. Then the line integral of our vector field f over this curve C is given by taking the difference in the values of my potential function little f at r of b. So what is r of b here? R of b would be the terminal point of my curve. Our curve is defined by this vector function r of t, and the terminal point is given by t equals b. And then we take the difference in that value of our function at the terminal point of the curve. We subtract from it the value of our potential function f at r of a. Now, r of a is the initial point of our curve. We take the curve defined by r of t and look at its initial point where t is equal to a. So in short, here's what this theorem says. It says that we can evaluate the line integral of a conservative vector field by finding its potential function f, as long as we know the value of the function at the endpoints of our curve. So this is sort of similar to the fundamental theorem of calculus. The fundamental theorem of calculus said if we're trying to find the definite integral of some function f of x with respect to x on an interval from a to b, we would need to find an antiderivative of that function, let's call it capital F of x, and we would evaluate from a to b. So that is, we evaluate our antiderivative at the terminal point of our interval b, and we subtract the value of the antiderivative at the initial point of our interval a. So this works very similar. It says that as long as we have a conservative vector field, if we can find a potential function, we can evaluate our line integral by looking at the difference in the values of our potential function at the terminal and initial points of our curve. So this often saves us a lot of work in evaluating line integrals because we saw in the last section, 6.2, that certain line integrals can be a little difficult to evaluate. So let's look at an example that makes use of this fundamental theorem. So here we are given the vector field f of xy. It's two-dimensional. So here its component functions are p and q. And in part A, we are asked to show that this vector field f is conservative and find a potential function for f. So to show that this thing is conservative, we would use our cross partials test. So that is, we look at the partial derivative of p with respect to y, which would be equal to 4y minus 36x cubed y squared. And we see if that's the same as the partial derivative of q with respect to x. So here, partial of q with respect to x is 4y minus 36x cubed y squared. It is indeed the same value. So since these cross partials are equal to each other, we can say that our vector field, f of xy, is conservative. by the cross partials test. So that means that this vector field is the gradient of some potential function, and we're asked to find that potential function. So we know in order for our field to be the gradient of some potential function, the derivative of that potential function with respect to x has to equal my first component of the given vector field. That is 2y squared minus 12x cubed y cubed. And the partial derivative of f with respect to y is equal to the second component of our given field. That is 4xy minus 9x to the fourth y squared. So if we know the partial derivatives of our potential function, we can find the potential function itself by finding antiderivatives of one of these partial derivatives. So let's look at it. One way that I could find f would be to look at the antiderivative of the derivative of f with respect to x integrated with respect to x. So here, finding our antiderivative of this function with respect to x, we have 2xy squared minus antiderivative of 12x cubed is going to be 3x to the fourth times my constant y cubed on the end, plus a constant with respect to the variable x, which would be any function that depends only on y. Let's call it g of y. Now, in order to solve for this g of y function, we're going to use the condition that we're given for the partial derivative of f with respect to y. So making use of that condition, if we take the partial derivative of f with respect to y for the function that we just found, we would have 4xy minus 9x to the fourth y squared plus the partial derivative of, or the derivative of this g of y function with respect to y, which we will call g prime. And we note that that must equal the value that we were given for the second component of our vector field. That is 4xy minus 9x to the fourth y squared. So we can compare on both sides of our equation. We see that we have this same term, 4xy minus 9x to the fourth y squared, which can be canceled. And we're left with the derivative of g, that is g prime of y equals 0. So if the derivative of this function is 0, that means that the function g of y must be a constant. And if we want the simplest choice for our constant of integration, that is the simplest choice for a potential function, we could choose this constant of integration to be 0, as we did in that last example. So what we find is a potential function, f of xy, would have the form that we found above. Here, it would be given by 2xy squared minus 3x to the fourth y cubed plus some constant, and if we don't have any other restrictions that have to be satisfied, we could choose our constant to be 0, in which case we would just have the following expression for our potential function. Now in part B, we are asked to evaluate the line integral of this vector field over the curve C, where C is defined to be any smooth curve that passes from 0, 0 to 2, 1. So let's think about this. We know that from our work in part A that this vector field is conservative. So to integrate a line integral of a conservative vector field, over some curve, we can make use of the fundamental theorem, this new result that we introduced. So I'll say here, by the fundamental theorem for line integrals, the line integral over the curve C of our vector field f dot dr can be evaluated by looking at the difference in the value of my potential function f at the terminal point of my curve, which we were given here as 2, 1, and the value of my potential function f at the initial point of the curve, 0, 0. So let's see what we have. If I substitute 2, 1 into the potential function that we had above, well, it was given by 2 times x, so here x is 2, times y squared, so 1 squared, minus 3 times x to the fourth, so that is 2 to the fourth, times y cubed, so here 1 cubed, and then we subtract the value of our potential function at 0, 0. Now plugging in 0, 0 for x and y, we're left with 0. So let's see what we end up with. Our first term here is 4 minus 3 times 2 to the fourth is 16, so here minus 48. So we're left with negative 44 for the value of this line integral of our vector field. So this fundamental theorem gives us a much easier way to evaluate a line integral of a conservative vector field, so we don't have to find a parameterization of our curve that connects these points and use our method from the previous section. Now notice one thing that's being implied here by the fundamental theorem for line integrals is that it doesn't matter what the curve looks like that connects our endpoints. So here in part B, we were told that this is going to be the value for any smooth curve which connects 0, 0 to the point 2, 1. So in this example, let's think about what this is implying. If we have the point 0, 0 and the point 2, 1 in the plane, it doesn't matter what shape of curve we have. So one possible curve might be the line segment that connects those points. We could call that curve C1. And the value of the line integral along this curve would be negative 44. Now, if we consider a different curve, let's say we have this curve, C2, which connects 0, 0 to 2, 1, the value of the line integral along that curve will also be negative 44, because the fundamental theorem of line integral says it only matters the value at the endpoints of our curve. So we could consider all sorts of odd-shaped curves here, as long as our curve is smooth. And we would get the same value for the line integral along any one of these paths that connects that endpoint. To describe that property of conservative vector fields, we can introduce a little terminology here. So here's what we have. If f is a continuous vector field with domain D, we would say that the line integral of that vector field over a curve C is said to be independent of path if the line integral of our vector field over a curve C1 is equal to a line integral over the curve C2 for any two paths, C1 and C2 in D, that have the same initial and terminal points. So a line integral of a vector field is said to be independent of path if the value of the line integral is the same for any two paths connecting the same 2 points. So to illustrate that, let's say that we have within some domain D, two points, some initial and terminal point of a curve, and we have some curve C1, which connects those points, and we have a different curve, let's say C2, which connects those same 2 points. Then this line integral is independent of path if the line integral of our vector field over the first curve is equal to the line integral of the vector field over that second curve. This is called independence of path. So what we saw from our last example is that the fundamental theorem for line integrals says that line integrals of any conservative vector field is independent of path. So the fundamental theorem said that we only need to know the value of our potential function at the endpoints of the curve. It doesn't matter what the curve looks like in between those endpoints. So line integrals of conservative vector fields are always independent of path. Now another nice property which we can make use of here follows directly from the fundamental theorem for line integrals. It says that if f is a conservative vector field, then the line integral of f over the curve C has to be 0 for every closed path C in our domain. So here, one thing that I want to point out is a little notational difference in what we've seen so far. Notice that this line integral here of C is denoted using this integral symbol with a little circle over it. So that integral with a circle symbol over it is used to denote the fact that our curve C is a closed curve. That is, its initial point is the same as its terminal point. So anytime you see a integral that has that little circle over it for a line integral, that's just using to denote a closed curve. So here, this notation denotes a closed curve. So the reason that that would hold is the following. Let's say that we have some closed curve C where our initial point and terminal point are the same. So that is, if we consider this curve as the graph of a vector function from t equals a to b, the value of the point at time t equals a is the same as the value at t equals b. So if we have a conservative vector field, the line integral over that closed curve by the fundamental theorem for line integrals is given by the value of the potential for that conservative vector field at the endpoint r of b and the value of the potential function at r of a. But for a closed curve, r of a and r of b are the same value, so we're taking the difference in the value of the function at the same point, which must give us 0. For any line integral of a conservative vector field, if we're integrating over a closed curve, we must get a 0 value. So this gives us another way to determine whether a vector field is conservative. If we look at the plot of our vector field, we can see sometimes easily whether the field is conservative or not. So as an example of that, we are asked the following: is the vector field shown in this figure below conservative? And then explain our answer. So let's think about how we could justify this. We know that the line integral of a conservative vector field must be 0 over any closed path through that field. So let's consider a particular closed path. So say that we start here, and we're considering the path described here, traversed in this order. Let's call this curve C. So we can see that for our vector field, as we are traversing this curve, we are always moving in the direction, or along the direction, of these vector field arrows. So this line integral would be positive. So here, if we were to consider the line integral C over this closed curve, so we would use a little circle notation over our integral of this vector field, f dot dr, it would be positive. So that is, we have some value other than 0, but we know for conservative vector fields, the integral of that field over any closed path would have to be 0. So here, since we have a line integral which would be non-zero, f is not conservative. It would contradict the fundamental theorem for line integrals if this were conservative. All right. So let's look at another example. In this last example, we are asked to consider a force field, so some vector field in 2 dimensions, which represents the force acting on an object at a point in the plane. And notice for this example that x cannot be equal to 0, since both component functions of this field involve division by x. So what that means here, before we jump into the problem, if x can never be equal to 0, geometrically, when we're thinking about this force field, in moving an object along a curve, we cannot consider any curve that would cross the x-axis. If we were to have some curve C, which crosses the x-axis, that means at some point x was made equal to, or excuse me, I'm sorry, it cannot cross the y-axis. If it crosses the y-axis, then we have points where x is equal to 0. So here we don't want any curve which is crossing our y-axis. Otherwise, our field would be undefined. So with that in mind, let's look at part A of this problem. We are asked in part A to show that this field is conservative and find a potential function for f. So for a 2-dimensional vector field, to show that it is conservative, we use the cross partials test. So here the partial derivative of p with respect to y is equal to 2y over x squared. And we ask, is that the same as the partial of q with respect to x? So here, partial of q with respect to x would be a positive 2y over x squared. It is indeed the same partial derivative. So what that means is that this vector field f is conservative. Now, in order to find a scalar potential, we're going to let the partial derivatives of the potential function f with respect to x equal the component functions of our vector field. That is, the partial of f with respect to x is equal to y squared over x squared, and the partial of f with respect to y is equal to negative 2y over x. So to find the potential function f of x and y, we could take the antiderivative of the partial derivative with respect to x, which was y squared over x squared, integrated with respect to x. So here we can think about this in the following way. Y squared over x squared is the same as x to the negative 2 times y squared dx. So for our antiderivative, we would have negative x to the negative first times y squared. So negative y squared over x plus some constant with respect to x, which would be any function that depends only on y. Let's call it g of y. Now to find that g of y function, we need to use the condition that we have on the partial derivative of f with respect to y. So here, our partial of f with respect to y is then equal to negative 2y over x plus g prime of y, which is equal to the value that we were given from above, negative 2y over x. So we see by comparing the terms on our left and right hand side, this negative 2y over x on both sides cancels. We're left with g prime of y equals to 0, which means that g of y is equal to some constant. And if we don't have any restrictions on what must be satisfied by our potential function, we can choose this constant to be any arbitrary constant. So let's take the easiest choice of 0. Therefore, we find that our potential function f of x and y would be equal to negative y squared over x plus any constant. Now, if we choose our constant as 0, we have our potential function is negative y squared over x. So now that we have our potential function, we can answer some questions about this force field related to line integrals. So in part B, we are asked to find the work done by this force field in moving an object from the point 1, 1 to the point 4, negative 2. So recall here that the work done by a force field in moving an object along a curve is given by the line integral of that force field over the curve C. So here, since this was a conservative vector field, we showed in part A this was conservative, the fundamental theorem for line integrals says that this line integral can be evaluated by taking the difference in our potential function at the terminal point, 4, negative 2, and the value of our potential function at the initial point, 1, 1. So let's see what we have here. Plugging in 4, negative 2 to our potential function that we found in part A, we have negative 4 over 4, or negative 1, minus the value of f at 1, 1, which would be negative 1. So we have here negative 1 plus 1, or 0, for the work done by this vector field in moving our object along that curve. So here, the curve we were considering was any curve from the point 1, 1 to the point 4, negative 2. So our curve could have any general shape in moving from 1, 1 to 4, negative 2. as long as it does not cross the y-axis. That was the one restriction that we had on this curve. So we might find it unusual here that the work done by this vector field is 0. Why would that be the case? Well, if we were to plot this vector field, we would find that for certain points in the plane, our object, or our vector field, our force field, is acting against the direction of motion of our object. And at other points, our vector field or force field is moving with the direction of the trajectory of our object. So if we sum the values of this force along that path, we find that the sum would be 0, or the work done by that force field as our object moves along this curve is 0. So lastly, the last part of this problem says find the work done by this force field in moving an object along any closed path. So we know, since F is conservative, which we showed in part A, the work done, which would be the line integral of our force field, F, along some curve C, where C is any closed path. So here, if C is a closed curve, we use this circle notation over our integral. And since F is conservative, we know that the value of the line integral over any closed path must be 0. All right, so we have seen in this section that conservative vector fields have very nice properties. We had the cross partials test to see whether a two-dimensional vector field is conservative, which allows us to find a potential function for that vector field by thinking about the partial derivatives and how they're related to the components of our vector field. And if we're able to find a potential function for a conservative field, we can use it to evaluate a line integral, making use of the fundamental theorem for line integrals. And this fundamental theorem for line integrals says that any line integral of a conservative vector field is independent of path. That is, it only matters what the endpoints of the curve are. And the line integral of a conservative field over any closed path must be 0. So we're seeing that in this section, conservative vector fields have very nice properties related to their line.